Hi, this lesson is about polynomial functions and their graphs. So remember that a polynomial function will have exponents that are natural numbers. So the natural numbers are 1, 2, 3, 4, 5, etc. So you won't have any exponents that have negative numbers. You won't have any exponents with fractions or decimals in them. And so all of your terms um, could either be variable terms or a constant, but the term with the largest exponent will determine the degree. So an example like this one, this is considered to be a fifth degree polynomial with three terms in total. Two of them are variable terms, the first one and the second one, and the constant is 7. The leading coefficient is also 7, but that refers to the number right in front of the variable part that determines the degree. So again, the vocabulary is really important in math just as much as the math is. So make sure you understand what all the words mean so that when you're asked questions on homework or tests, you understand what you're being asked. The second example here, number 2, this will be an eighth degree polynomial. Again, the highest exponent is an 8. It has 4 terms in total. The first 3 are variable terms, and the constant is -5 or -5. So consider that a negative because of the minus. The leading coefficient here is the number in front of x to the 8th, which is -3. So being able to determine the degree and the leading coefficient will have a lot to do with how the graph of the function behaves. So that's the first thing we need to understand is how to identify the degree and the leading coefficient. To help us graph, we can use x-intercepts, which are also called roots or zeros, the y-intercept, the maximum and minimum points to help us sketch the graph of a polynomial. So remember, we talked about maximums and minimums when we were talking about quadratic functions. Quadratic fall under the umbrella of polynomials, but when you have a higher degree greater than 2, it is possible that you could have both maximums and minimums. Your graphs could be oscillating in different directions like this. So you could have multiple maximums and minimum points as you see like something like this. Okay, so here I have graphed on my graphing calculator app. I use Desmos. You can use a graphing calculator or any graphing calculator app that you prefer. I have graphed y equal to x to the third minus x squared minus 6x. This is a third degree polynomial. The leading coefficient is 1. You can see on the graph that I have 3 x-intercepts, one at -2, 0, another one at the origin 0, 0, and another one at 3, 0. The y-intercept is also the origin, so the origin is unique in that it is both an x and a y-intercept. And I do have a maximum value here. This is the approximate value at -1.12 and 4.061. So I wrote that's about -1.4. And then I have a minimum down here at 1.786 and -8.209. So that is about 2, -8. So oftentimes it won't be easy to find maximums and minimums. You actually need calculus to be able to compute what the maximum and minimum values are. So using a graphing calculator or an app will help you identify those maximum and minimum points. So this one has both a maximum and a minimum. And they would be considered to be relative or local maxes and mins because this is not the highest value overall. There are infinitely many values greater than it, and this would be a relative or local minimum because it is not the lowest one overall. It is the lowest point on a small interval to the left and right of that point, but there are infinitely many points that are actually smaller than that minimum point. So They would be a relative or a local maximum and a relative or a local minimum. Okay. The graph of a polynomial is considered to be continuous. So continuity has a formal definition, but we're not going to really formally define it just yet. But basically, what it means is that there are no breaks or holes, no kinks, cusps, or corners anywhere in the graph. It's just a smooth, continuous graph that you could draw without picking up your pencil or pen. So that's what smooth means. You won't have any sharp corners like this. Like that would be considered a kink. So it would be, something like that, like something smooth without any breaks or holes in it. So that's what continuous polynomial functions will look like. Some are very simple, like a line. That's a polynomial. That's smooth, nothing sharp there. Parabola is also a polynomial. That's just a smooth graph. And then we have our higher order polynomials like this third degree polynomial. Okay. So here are some examples. So the first example in orange is a polynomial function. It's smooth and continuous. The second example here in blue, that is not a polynomial function. There is a break right here at 0. So I have a point here at when x is 0, and then I have an open circle here. You cannot draw this graph without lifting up your pencil or pen. So there's a break there. That break is called a discontinuity. This one here in green is not a polynomial. Although it is continuous, you can draw it without picking up your pencil. It has a kink or a cusp to it. So this little kind of squeezed part here makes it not a polynomial. And this one is also not a polynomial. This is not smooth. It's got like some sharp corners here, 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 and here. So only the first one would be an example of a smooth continuous graph, which is what is represented um, by a polynomial function. So like I mentioned earlier, determining the degree and the leading coefficient will allow you to identify some behavior about the graph, specifically the beginning and ending behavior of a graph. So in this chart, it's kind of summarized for you. So if your degree is odd and your leading coefficient is positive, like this one, this is a third degree polynomial with a leading coefficient of +1, then your graph is going to drop to the left and rise to the right. So this would be an example of what an odd degree and a positive leading coefficient looks like at the beginning and at the end. The higher this degree is, the more likely it is that it's not just this kind of S-shaped looking thing. It could be more complex, like something like this, but the beginning behavior would be the same. It would drop left and rise to the right whenever your degree is odd and your leading coefficient is positive. When your degree is odd and your leading coefficient is negative, it's going to have the opposite relationship. This is an example, and this is what that graph would look like. It rises to the left and drops to the right. When you have an even degree, like a degree of 2, 4, 6, 8, etc., and your leading coefficient is positive, then the graph will rise to the left and to the right. So my example is just the parabola y equals x squared, which we've drawn many times in previous lessons. That rises left and rises right. So the beginning and ending behavior are the same when you have an even degree. But then it's the opposite behavior here. Degree is even, leading coefficient is negative. So this would be my example. That's an upside down parabola. So that drops left and drops right. So the higher this degree is, the more likely that there'll be more oscillation, but the beginning and ending behavior would be the same. So this would also be something with um, an even degree and a negative leading coefficient. It drops left and drops right, but in between it has these other peaks and valleys, which we're calling our maximum and minimum points. Okay, so we're going to use the information in that chart um, to describe the beginning and ending behavior of the following. So I have 2x to the fifth plus x to the fourth minus x plus 3. So without graphing it, although I did provide the graph for you so that you can see, I'm going to refer back to this table. This has a leading coefficient that is positive and a degree that is odd. So that is this right here. That means it drops left and rises to the right. So the graph looks like this. That's exactly what it's doing. It's dropping left and rising to the right. So the way this is described is as x approaches negative infinity, meaning the further you go this way, f of x is also going towards negative infinity. But as x gets bigger, x goes towards positive infinity. These values, f of x goes towards infinity. So that's what we consider to be the beginning and ending behavior of this function. And because I graphed it, you can also see that there is a maximum point here and a minimum point here. Without the graph, you would have been able to answer the same questions about beginning and ending behavior just by using the table above. Okay, part B is y equal to negative 3x to the sixth plus 2x to the third minus x. The leading coefficient is negative, the degree is even. So that's this one right here. Even degree, negative leading coefficient. So that means that it drops left and to the right. So as x approaches negative infinity, f of x also goes to negative infinity. So dropping left means it goes down. So this is what it means to go down. It's going towards negative infinity. And as x approaches infinity, f of x also approaches negative infinity. Remember, the beginning and ending behavior are the same when you have an even degree. And again, this is the picture for this graph. That's what, for this function, that's the graph of it. So you can see as x becomes more and more negative, your f of x becomes more and more negative, and the same thing here, as x becomes more and more positive, this is also approaching negative infinity. So that's what it means to say it drops left and drops right. Okay, so in this next example, so this would be helpful for you to memorize, right? This would be a helpful table for you to memorize so you can visualize what a graph would look like with just this basic information. Okay, so here, this problem in green, find the intercepts, then sketch the graph for y equal to negative 3x to the fifth plus 5x to the third minus 2x. The y-intercept is always the easiest one to find because you find the y-intercept by replacing the x's with 0. So if you plug that in, everything just becomes 0. So 0, 0 is your y-intercept. It will also be an x-intercept. Remember, that's that unique point. That's both an x and a y-intercept. But that doesn't mean it's the only x-intercept. So to find the x-intercept, you have to do the work on the next few lines is you set this entire equation equal to 0. This is factorable. It has a common factor of x. I decided to factor out negative x, which leaves me with negative x times 3x to the fourth minus 5x squared minus 2. So I can factor what's inside of the parentheses even further. So that factors into 3x squared plus 1 times x squared minus 2. So if you solve each factor, this one will become 0. This one will become plus or minus root 2. I didn't solve this one because I know that if I solved it, you would subtract 1 from both sides, then you would divide by 3, then you would take the square root, And the square root of a negative number is an imaginary number. So this would be plus or minus I root 1 over 3. This is imaginary. This is not a real number. So therefore, you can't graph an imaginary number on an xy plane, so they would not be considered to be x-intercepts. They are solutions to the equation, but they are not x-intercepts. So you only want the real numbers. So my x-intercepts are 0, 0, negative root 2, 0, and positive root 2, 0. So we have 3 points on the graph. Okay, and then again, so that I'm sure that I have a good picture, I'm going to use what I learned, or what we learned together in this chart above. The leading coefficient is a negative and the degree is odd. So this should be rising to the right and dropping to the left. So it should be going, it would do something like this. Something else is going on in the middle, but this is the beginning and ending behavior. So once I put these points in and use this information, I plotted negative root 2, 0, 0, 0, and positive root 2, 0. Root 2 is between 1 and 2. Negative root 2 is between negative 1 and negative 2. And then when you connect them, you can see that it rises to the right. This goes towards infinity, and drops to the left. That goes towards negative infinity. So again, this is how we describe the beginning and ending behavior by using the leading coefficient and the degree. So if that's confusing, just refer back to the table. This behavior of the graph is exactly the way the table describes that, what your expectation is. All right, if we call C a zero of a polynomial, remember a zero is just another word for an x-intercept. So if we call C the zero of a polynomial, then P of C equals 0. And that is true. Remember, when we found these, we let the function equal 0. So, when x equals c, that's considered to be a solution of the original equation equal to 0. And when that's true, x minus c is considered to be a factor of the polynomial. So whatever c is, take the opposite sign of that and combine that with x. So x, if c is positive, then it would be x minus c. And if c is a negative number, then your factor would be x plus c. So you always put the opposite sign along with the x, and that's considered to be a factor of the polynomial. And that information is helpful to break down polynomials further. Sometimes that provides us with more information to get a good sketch. All right, so here we want to sketch the graph of p of x equal to the product of x plus 2, x minus 1, x minus 3, and x minus 5. This is a very convenient way to present my polynomial because it is already completely factored for me, which means that all I have to do is set each one equal to 0. And if I take each one of these are all linear factors, and set each one equal to 0, I get several solutions: negative 2, 1, 3, and 5. Those are all zeros, or x-intercepts of the polynomial. So I know my x-intercepts. I can easily find y-intercepts by replacing all of the x's in here with 0. And that's the work that I did here, which just means that you're multiplying 4 numbers together: 2, negative 1, negative 3, and negative 5, which gives me an answer of negative 30. So I have these 4 points. I have this point. And then I can put this together along with what I know about the original function. This is a 4th degree polynomial because even though I didn't expand it, if you were to multiply these out completely, you would have x being multiplied 4 times. So this would be a 4th degree polynomial, and all of the coefficients in these factors are 1. So my leading coefficient would be positive. So I know that I have an even degree, positive leading coefficient, and then I have several points to plot. So here are my points: negative 2, 0, 0, -30 is down here. That's your y-intercept. 1, 0, x-intercept. 3, 0, x-intercept. 5, 0, x-intercept. And then using the information, it's a fourth degree polynomial, should be rising left and rising right. Connect all your dots together, and that's what your polynomial looks like. Exactly how far up you go here or how far down you go here, you're just going to estimate that for now. Because again, we need calculus to compute what those maximum and minimum points are. Um, which isn't something we know how to do yet. So you would need a graphing calculator to get you a more precise idea of what these two values are. But the general shape you can get just from knowing these x and y intercepts and understanding the behavior using the degree and the leading coefficient. And again, this is the way you would describe the behavior using this notation. So as x approaches negative infinity, f of x goes to infinity, and as x approaches positive infinity, f of x also goes to infinity. So when the factors are repeated, that also impacts something called the multiplicities of the zeros, which affects the graph. And this, we haven't seen any examples like this just yet. So this chart summarizes it for you, but then I'll show you some examples. So if your multiplicity is odd, meaning a factor only shows up an odd number of times, so 1 time, 3 times, 5 times, those are all odd numbers, then the root or the zero or the x-intercept associated with that root would cross the x-axis. It would go right through it. So this is my example. If you were to factor this works out to be x minus 4 and x plus 1. I have two unique factors here, both raised to the first power. First power means it's odd, which means that at x equal to 4 and at x equal to -1, the graph is going to go through those two values. When your factors show up an even number of times, meaning 2, 4, 6, 8, etc., then you're going to just touch the x-axis. It's not going to go through it. So my example is this one. If I were to factor that, I would get x plus 2 times x plus 2, which you know is the same as x plus 2 to the second power. This is an even number. So when I plot my 0, it's only going to touch the graph at -2, 0. It's not going to go through the graph at -2, 0. So we'll see some examples here. So this was the first one in the table. It has two solutions at 4, -1. This is a parabola. And so at 4 and at -1, I plotted my two x-intercepts. So the parabola goes right through those two x-intercepts because the factor only shows up once. Again, it's a second degree polynomial with a positive leading coefficient, so it's rising left and rising right. They're both going to infinity, but the multiplicities tell you whether it's going through these points or just touching it, almost like bouncing off of it. They're going through because of the multiplicities being odd. For the next example, the same one I had here, you get x plus 2 and x plus 2. That means I have the same factor twice. So -2 is an x-intercept. It's also a second degree polynomial with a positive leading coefficient, so it's also rising left, rising right. But instead of going through -2, it basically just touches it at -2 and then continues going back up. So it goes down and back up. It doesn't pass through it the way it did here and here because I had the same factor twice. So if the same factor comes up an even number of times, it's only going to touch the x-axis. So think of it as like bouncing off of the x-axis, not going through it. And here's the explanation. Okay, so here we want to sketch the graph of p of x equal to negative 2x to the fourth minus x to the third plus 3x squared. So we're going to use a lot of the information that we just talked about to come up with a good graph here. So I'm going to find my y-intercept. This one also has a y-intercept at 0, 0. I'm going to find x-intercepts, which are also called zeros, by setting the whole thing equal to 0. Negative x squared is a common factor, leaving me with negative x squared times 2x squared plus x minus 3. This is factorable. And if you don't remember how to factor, please make sure you go back to algebra notes, lessons to refresh your memory. Factoring does come up a lot in pre-calculus as well as calculus. So that factors into 2x plus 3 and x minus 1. That means I'm going to get 3 unique solutions. So I have, this one works out to be x equal to 0, but this one has a multiplicity of 2 because of that exponent. This one works out to be negative 3 halves, and this one works out to be 1. Those both have a multiplicity of 1 because those factors only show up once. This is to the first power and this is to the first power. That's what determines the multiplicity. So we know that the leading coefficient is negative and the degree is even, which means it's going to drop left and it's going to drop right. Okay, so now I can use what I know about the multiplicities and that information. I graph these 3 points. So negative 3 halves, 0 is first, 0, 0 is second, and 1, 0 is the third point. So I drop left, so that means I'm going to go up, go through the negative 3 halves because the multiplicity is odd, then come back down and then bounce here at 0, 0 because the multiplicity is even, and then go back up and then down again and go through that 0 because the multiplicity is odd. And here is your beginning and ending behavior. So knowing the multiplicities is really helpful so that you know whether you go through the point or just touch the point and then continue in the other direction. Okay. Here's another one. Here we want to sketch the graph of p of x equal to x to the third minus 2x squared minus 4x plus 8. So I found the y-intercept first. That's when you plug 0 in for x. So 0, 8 is your y-intercept. Then I'm looking for x-intercepts. That means you take this whole equation, set it equal to 0. This one has 4 terms. You can actually factor it by a technique called factoring by grouping. So again, if you don't remember these techniques of factoring, you do need to go back to algebra. So the first 2 have a common factor of x squared, leaving me with x squared times x minus 2. These 2 have a common factor of minus 4, leaving me with minus 4 times x minus 2. Then x minus 2 is the common factor from those products, leaving me with x minus 2 times x squared minus 4. This is the difference of perfect squares, so that factors even further. So I get x minus 2 times x plus 2 times x minus 2. So that means x minus 2 shows up twice, and x plus 2 shows up once. When you solve those factors, the one associated with this one is 2, and that's got an even multiplicity. And this solution is negative 2, that's got an odd multiplicity. So my x-intercepts are at negative 2, 0, and at 2, 0. Okay. So leading coefficient is positive, degree is odd, so it should be dropping to the left and rising to the right. That's from the table I showed you earlier. And then I put these points together. Here's negative 2, 0. Here's 2, 0. Here's my y-intercept at 0, 8. It goes through negative 2, 0. Again, this is dropping left, means it goes to a negative infinity. Goes up, then comes back down, and it bounces here at 2. It doesn't go through it because the multiplicity is even, and then goes back up. And so, and this is going towards infinity. Okay. So this is probably a lesson that you're going to want to go back and write some things down, try to memorize the information in the tables. Probably have to review it more than once to keep this all straight. So remember, maximum and minimum values are also called extreme values or extrema. So as I've mentioned a couple of times, you need a graphing calculator to find them, or you can use an app. And again, this is the one I use. You can use any app you want. If you do have a graphing calculator, these are some of the more, I guess, common models. TI stands for Texas Instrument. Model 83, 84, and 86. Those are 3 different models, but their keys are very similar, their functionality is similar. So I gave you some directions as to how to use them to find zeros or x-intercepts, also to find maximum or minimum values, so you can read them if you choose to use them and if you have that tool. But you don't have to go out and buy a graphing calculator if you don't want to. This is free and provides you with some good information. So that's it for this lesson. Good luck.